Okay, so I'm going to be talking about generalization for adaptively chosen estimators via stable median. And I'd like to start off by giving you a sort of motivating, fun story. So let's just imagine that you decide to enter a machine learning competition, and the task of that competition is to classify images as, happy or grumpy or something like that. And the competition organizers have a test set of n examples, and you submit submissions, and they give you a score based on the fraction that you correctly classify. Now, unfortunately, you're an incredibly lazy programmer, so you just submit random classifiers. So you use a hash function as a classifier or something like that. And unfortunately, this is only going to get you about 50% accuracy. But you're persistent, idiot. So you keep trying. And sometimes you get a little bit more than about 50% just by chance. Sometimes a little bit less than 50%. But this really isn't going to work. You just keep sitting there spamming the submission server with lots and lots of submissions. And unless you have exponential time, this just isn't going to work. So you're not going to get very far. But you have a trump card up your sleeve. So you look at these submissions and you pick out the ones that did ever so slightly better than average. And what you're going to do is combine these submissions into one big submission that takes the majority vote of these random classifiers. You submit that, and hey presto, you get a high score. How did that happen? So this is actually a general fact. If you're able to do this with the number of submissions being super linear in the number of examples in the test set, this is going to happen. And the problem is that your kth submission depends on the scores of the previous submissions, which in turn depend on the test set, and therefore you're able to overfit because you've got this strange dependence going on. And this is the problem of adaptivity. So could the contest organizers do something to prevent people coming along and just gaming the system like this? And the good news is that there's actually a way that they can guarantee a constant level of accuracy. That means that each reported score is within, say, 5% of the true score of that submission. And they can do this as long as the number of submissions is about quadratic in the number of examples they have to test them with. This is actually the optimal relationship between the number of submissions and the test set size. Now, what does this plus or minus 5% accuracy mean? Now, if I tell you that your score is between 45% and 55%, that's pretty good. That's telling you that your submission is approximately useless. But that, of course, is very different if I were to tell you that the score is between 90% and 100%. Those two numbers are quite different. So one of the things that this work does is it shows how to, avoid this difference. So we're going to show you how to get accuracy that scales with the variance of the data. So if the true accuracy of your estimator is p, then we can guarantee that the reported score is going to be within something that scales with the standard deviation of that. Now, of course, these results are not specific to just 0, 1 valued queries. They can extend to arbitrary real value functions. Okay, so that's the high-level idea of what we're talking about. Now, I do want to tell you that adaptivity is not just something that gets cooked up, like this example I showed you. It actually appears as a real problem, both in the empirical sciences and in actual machine learning competitions. There's some evidence that people have been trying to do more sophisticated things. Okay, great. So I've given you the opening sort of motivation. Now I want to sort of delve into the model, which comes from previous work, and then move on to results. So what are the key characters in the model? So we start off with a population, which we think of as a probability distribution. And there's someone who's interested in that population. And they have various questions, like what fraction of the population is correctly classified by my submission? Or they could have really sophisticated queries about neural nets or whatever. But for now, we're just going to talk about real-valued queries. So the analyst specifies a function, and they want to know what the expectation of that function is. And in order to figure that out, they collect a sample from that population. They stick that into their computer, and then they submit a query, and they get an answer. And then they submit another query, and they get another answer. And they're going to do this for k rounds. Now, the key thing is the kth query is specified after the previous answers have been received. So query k depends on answer 1 through answer k minus 1. And that dependence is what's causing, that's what the adaptivity is. And just for comparison, in the non-adaptive model, which is what's usually studied, the queries are all specified at once, and then the answers come back at once. And in this case, we don't have this dependence between the queries and the answers. So what does it mean for my answers to be accurate? So the simplest notion of accuracy is just additive error. So if I tell you that each answer is within 5%, say, of the desired answer, that would be an additive error guarantee. In this work, we're going to look at an error that depends on the variance of the query. So we're going to say that the answer is accurate if it is within 1 over square root t standard deviations of the desired answer. And that is what you would get if you just had t fresh samples and used those fresh samples to evaluate the query. Okay, so now I've specified to you what the model is. Let's talk about the results. So the previous work has shown how to get additive accuracy. And the relationship between the sample complexity and the number of queries is about square root k, and this is the optimal dependence on the parameter k. And in this work, we extend these results, and we are able to show that we can get accuracy that depends on the variance. And you can, obviously, if t is about 1 over alpha squared, then these results dominate the previous results. Now, just as a comparison point, if we look at the non-adaptive setting, where we can just use a union bound, then we can just use a concentration inequality like Chernoff or Hofding or Bernstein, and we get a logarithmic dependence on the number of queries k. So some key points I want to emphasize is that previous work, the accuracy scales with the worst case bound that you have on your query values. And in this case, we're going to get that down to the standard deviation. And the worst case bound is essentially irrelevant. It does appear in some logarithmic factors, but that's much better than a polynomial dependence. Now, at the beginning, I gave you this example of evaluating a classifier. That's a very simple query. Value is 0 or 1. And in that case, we're able to get an accuracy guarantee that scales with square root of p. But our results are not specific to just 0, 1 value queries. We can handle arbitrary real-valued queries. And we're also able to use lots of other extensions that have been used in previous work. So that we're able to do a lot of things with this underlying basic technique. So maybe the take-home message I want to push from this work is that, at least as far as real-valued queries go, we can simulate having k batches of t fresh samples using only square root k times t samples. You'd think you'd need k times t samples to do that, but actually we can improve that, and that's kind of magic in my mind. Okay, so let's talk about how we might actually construct this. So we're going to use a couple of tools. So the first is the well-known connection between stability and generalization. And the specific form of stability that we're using is differential privacy, which obviously was invented for different purposes, but has been shown to be very useful for ensuring generalization in the setting where you're doing adaptive data analysis, because it is able to compose adaptively. And the other ingredient that we're adding is the median of means technique. Now, this gets used in many places because you're able to exploit some additional properties of the median. Now, we don't use exact median. We're going to use an approximate median, which is going to allow us to satisfy differential privacy. So these are the two high-level ideas that go into making this work. We're going to use differential privacy and the median as opposed to the mean. So maybe a schematic view of our algorithm is, you take your sample. So for each query, we're going to do the following. We take our sample of n IID samples, and we split it into m batches, each of t samples. And we evaluate the query on each of those samples. We have the empirical mean of the query. And it's going to give us values, which we'll call V1 through Vm. And then we stick it into this box, which is the approximate median. And that's going to give us the answer. That's the answer we'll be reporting. So just by comparison, the previous work would take all of the samples, compute the empirical mean once, add some noise from a Gaussian or a Laplace distribution, and report that. So the difference is that we're splitting the sample up and using an approximate median. So what is an approximate median? So you have your values V1 through Vm, and these are real numbers, so you can plot the empirical cumulative distribution function of those. And that's going to be this jagged line here. So your value V1 is here, V2, V3, if they're in sorted order. And you see that you get this thing. And these are coming from some underlying true distribution, which you'd get if you used fresh samples to evaluate the query. And that's this red line. Now, a true median would be if you look at the 0.5 and you find the point on the curve that gets it. That's the median of the distribution. An approximate median, instead of looking at 0.5, you just look at some interval around 0.5, and then you look at what values would fall into that interval in terms of the CDF. So these are things that are between the 0.4 and the 0.6 quantile. And you get empirical approximate medians, which is this blue interval, and you get the true approximate medians. And the key step is that differential privacy, so if you're ensuring that you've got differential privacy throughout the whole process, this is a stability guarantee, and that ensures that the true and the empirical CDFs are close in L infinity distance. So these functions are close. And that's really the generalization guarantee that we're going to be using. And the other ingredient, of course, is that we have actually got very good algorithms for computing differentially private approximate medians. Okay, so I'll just give you a very simple example of how a differentially private approximate median would work. So you have some empirical CDF, and you're going to use that to create a probability distribution on outputs that you're going to sample. And it's going to look something like this. So if you're true, so if these dotted marks are your values V1 through Vm in sorted order, you look at the true median, that's the interval that you're going to be outputting with highest probability, things that are one thing away from the true median, you're going to output with slightly less probability, and this is going to decay exponentially. So this is a very simple algorithm for computing an approximate median. Unfortunately, you're going to have to pay logarithmically for the range of possible values and also the precision with which you want to output those values. And that's sort of unavoidable, but we can improve that to a much smaller function like 2 to the log star, which I don't know if you're familiar with log star, is basically a constant for practical purposes. Okay, so those are simple algorithms for computing the approximate median. So we plug that in, and that's how our algorithm works. So the key win that we're getting from using a median instead of just adding everything up and getting a mean is that the CDF, the empirical CDF, can't change very much if I were to change one of these blocks of samples. Whereas if I had the mean, then changing one of those samples, I could move that quite a lot, and that'll affect the mean quite a lot. Sorry. Okay, so there are a lot of extensions for this work. So the one that I want to mention first is that we're able to extend this to arbitrary real-valued estimators. So for example, if I wanted to compute the variance of my distribution, that's not a linear function, so I'd actually have to take in a bunch of samples. We're able to handle that. Basically, any function that outputs a real value, we're able to get guarantees at scale with the variance. Another very interesting extension that appeared in earlier work is what's called the reusable holdout technique. So I ask you a bunch of queries that ask for verification rather than just answering the output. So instead of just submitting a query, I also submit a guess to the answer, and you're going to tell me yes or no, is that a good guess? And there are also more sophisticated algorithms that can exploit the fact that if you have very low dimensional data, we can actually improve the sample complexity to be logarithmic in K, but you have to have some additional dependence on the dimension. So there's a lot of interesting extensions that can be built on this underlying technique of using approximate median. Okay, so just reiterating the key points. The take-home message I want to tell you is that we're able to simulate having K batches of T-fresh samples, whereas previous work would have only given you additive guarantees. We're able to really get you what you would get if you had fresh data for each query. All right, thank you. So the question is the dependence on the domain size and the precision necessary? So we know that it's necessary for differential privacy. I would assume it's necessary here, but we haven't proved a necessity condition.